Reactions of indeterminate beams by moment distribution method. So the general concept is that this was originated by Hardy Cross in 1930 in a paper entitled Analysis of Continuous Beams by Distributing Fixed End Moments. It is also used to analyze all types of statically indeterminate beams subjected to bending. And also, the moment acting on the beam of a member is the algebraic sum of the four effects. So these are the four effects of moment distribution. Number one, the moment due to the loads on the member if the member is considered as a fixed member or fixed end beam. So we're going to have a clockwise positive and counterclockwise to be negative fixed end moment. So here are the samples of fixed end moments in every segment. From A to B, segment A to B, and the left side it's going to be a negative MA since that's a counterclockwise, and on the right side it's going to be positive since that's clockwise. So the left moment will always be a counterclockwise, and the right moment or at the right portion moment would always be in clockwise. As you can see, the P force is applied at the middle of the length L. Therefore, the end moment or the fixed end moment is PL over 8. And they're actually just the same for MA and MB, but of different sign. Another, we have this type of P force which is applied a certain A distance from A and B distance from capital letter B, as you can see in the figure. So on the left side, it's going to be again counterclockwise, and the right side would be a clockwise direction. And as you observe, MA is different from MB, and for MA, it's going to be PA times square of B over the square of L, while MB is P times the square of A times B over the square of L. The third one is the distributed load uniformly. So from segments A to B, again, as you observe, MA is counter and MB is clockwise. And they would have the same value but of different signs. So for MA, it's WL squared over 12. Likewise for MB, it's WL squared over 12. Here also, the distributed load is at the midway from A. So the value of MA, it's now 11W, the square of L, over 192. While on the right side, or MB, it's going to be 5WL squared over 192. And other example, for segment AB, there is a triangular loading. The maximum side of the intensity of the triangular loading is at point A, so therefore it's now WL squared over 20. And on the right side, which is at the least portion of the triangular intensity, it's WL squared over 30. So those fixed end moments that I had listed, you have to get familiar at least for you to be able to proceed with the second theorem for fixed end moments. So number two, the moment due to the rotation of the near end and the other end is fixed. So it is known as the stiffness or the K value. K value is also known as the rotational stiffness, and the end moment required to produce a unit rotation at one end of the member while the other end is fixed is I over L. So to compute for K of a certain segment, then we'd be able to get it from I from a segment over the length of the segment. The third one, effect, is the moment due to the rotation of the far end, and the near end is fixed. So this is now attributed by the distribution factor, or dF. So a dF of a certain segment is a ratio of the stiffness of this particular end over the summation of the stiffness of the other end and its end. So again, if we have a if we are going to get the distribution factor of AB, then it's going to be the stiffness of AB over the stiffness of AB plus the stiffness of BA. So it's something like that. If we need to get the stiffness of BA, then distribution factor of BA, then we need the stiffness of BA, which is KBA, over the stiffness of BA, which is KBA, plus the stiffness of BC, or the KBC. That's how to get the distribution factor DF. Number 4. The moment due to the relative translation between two ends of the member is known as the carryover moment, or the COM. To get the COM, it is actually the moment induced at the far end of a prismatic member equals 1/2 of the distributed moment at the near end, which is prevented by translation but allowed to rotate. Meaning to say, to get the carryover moment, or COM, all we need to get is 1/2 of the distributed moment. So we're gonna cross multiply it to get the COM, or the carryover moment.